In a storage room beneath a European university, inside a drawer that has not been opened in decades, a fragment of clay the size of a matchbox sits wrapped in acid-free paper. It is broken on three sides. Its surface is pitted, eroded, partially flaked away by 4,000 years of burial, fire, and time. To the human eye, it looks like rubble. To generations of trained Assyriologists, it looked like nothing at all. A dead end, a fragment too small and too damaged to be worth the months it would take to even attempt a reading. And then, in a research lab a few hundred miles away, a machine looked at it differently. This is not an isolated curiosity. It is the leading edge of a methodical, multi-year effort that has quietly reshaped how scholars approach the largest body of surviving ancient literature on the planet. For a century and a half, the study of cuneiform writing has been defined by an uncomfortable imbalance, an almost limitless supply of physical evidence, and a desperately limited number of human beings qualified to read it. That imbalance is the real reason so many fragments have been labeled, quietly and without ceremony, as too damaged, too small, or too isolated to be worth pursuing. Not because they had nothing to say, because nobody had the time to listen. This is the story of what happens when artificial intelligence is pointed at the oldest written language on Earth, and what it finds. To understand why a damaged clay fragment could ever be called unreadable, you first have to understand the scale of the problem historians have been quietly wrestling with for over a century and a half. Cuneiform is not a language. It is a writing system, the oldest one ever discovered. Pressed into wet clay with a cut reed stylus starting around 3400 BCE and remaining in active use for an almost unimaginable span of time, more than 3,000 years, stretching into the first century of the Common Era. During that time, cuneiform was used to write at least 15 distinct languages, including Sumerian, Akkadian, Babylonian, Assyrian, Elamite, Hittite, Urartian, and Old Persian. Sumerian is widely regarded as the earliest written language in human history, and Akkadian, its Semitic successor, became the diplomatic and literary language of the ancient Near East for 2,000 years, the language of law codes, royal annals, omens, medical texts, love poetry, and the world's oldest epic. Cuneiform was not always readable, even to scholars. For nearly 2,000 years after the last cuneiform sign was pressed into clay, no living person on Earth could read a single word of it. The script had to be cracked from scratch, and that effort itself took decades. In the 1830s and 1840s, a British Army officer named Henry Rawlinson spent years scaling a cliff face in Behistun, in what is now western Iran, to copy a trilingual royal inscription carved hundreds of feet above the ground by order of the Persian king Darius the Great. By comparing the Old Persian portion against the parallel Akkadian text, Rawlinson and a handful of other scholars, working independently, slowly reverse-engineered the cuneiform syllabary, sign by sign, through trial, error, and argument, across roughly 2 decades. It was, by any standard, one of the great intellectual achievements of the 19th century. It also meant that everything which followed, every fragment, every museum drawer, every uncatalogued tablet, had to be read using tools built from that same slow, manual, comparative method, refined only incrementally for the next 150 years. Hundreds of thousands of cuneiform tablets have been excavated since the 19th century, mostly from sites across modern Iraq and Syria. Most of them survive only as fragments. Corners, edges, shattered pieces pulled from the rubble of palaces and temples destroyed by war, fire, and the simple collapse of unfired mud brick architecture over millennia. They were dug up by 19th century excavators working with none of the careful stratigraphic methods modern archaeology demands, shipped to museums in London, Berlin, Istanbul, Philadelphia, and Baghdad, and then, in many cases, never looked at again. The British Museum alone holds well over 100,000 cuneiform tablets and fragments, one of the largest single collections in the world, and only a fraction have ever received a full scholarly publication. The Vorderasiatisches Museum in Berlin, the Penn Museum in Philadelphia, the Yale Babylonian Collection, and the Iraq Museum in Baghdad each hold tens of thousands more. They sit in drawers, thousands upon thousands of them cataloged in some cases by nothing more than a registration number and a one-line 19th century description, waiting for a scholar who may never come, because there simply are not enough trained cuneiformists alive today, and there never have been, to work through a backlog that size by hand. Consider the Epic of Gilgamesh, arguably the most famous work of literature to survive from the ancient world. A story of friendship, grief, and the human refusal to accept mortality, composed more than 4,000 years ago. No single complete tablet of it exists, not one. Scholars have spent nearly 2 centuries piecing it together from dozens of partial manuscripts, comparing handwriting, vocabulary, and breakage patterns by hand, on paper, one fragment at a time. The most famous single moment in that long reconstruction came in 1872, when a self-taught British museum researcher named George Smith was working through a pile of unremarkable Assyrian fragments and realized, mid-translation, that he was reading an account of a global flood, a boat built to survive it, and a bird sent out to find dry land. A story strikingly similar to the one in the book of Genesis, but centuries older, found on the broken tablet 11 of what would later be recognized as the Gilgamesh epic. According to the often repeated account from his colleagues, Smith was reportedly so overcome that he began tearing off his clothes in excitement. That discovery, made by one extraordinarily attentive human eye scanning one tablet, took years of training to even become possible, and decades more passed before the surrounding tablets of the epic were matched and translated. After all that effort, across nearly 2 centuries, roughly 2/3 of the text has been restored to readable form. The rest remains silent, scattered across collections that, in many cases, have never been cross-referenced with each other. That is the real mystery behind a headline like this one. It is not about a single tablet hiding a secret. It is about an entire civilization's literature, law, science, and religion broken into hundreds of thousands of jagged pieces, most of which have never been matched to their other half, and a quiet, methodical effort, only fully underway in the last several years, to see whether a machine could do what generations of human scholars could not do fast enough. The central figure in this story is Enrique Jimenez, professor of ancient Near Eastern literatures at Ludwig Maximilian University in Munich. In 2018, Jimenez and his team began a project with an almost absurdly ambitious goal: digitize every surviving cuneiform tablet fragment in the world's museum collections, and build the tools necessary to let a computer find connections between them that no human had ever spotted. The project became known as the Electronic Babylonian Library, or EBL. Its backbone is a digital tool called the Fragmentarium, a growing database of transliterated cuneiform fragments, searchable not the way a library catalog is searchable, but the way a genome is searchable. That comparison is not poetic exaggeration. It is, according to researchers on the project, structurally accurate. Cuneiform signs do not map cleanly onto sounds the way an alphabet does. A single syllable can be written in dozens of different ways, depending on scribe, period, and region. Jimenez has put it plainly. Cuneiform script is ambiguous, with up to 25 ways to represent the same syllable. That ambiguity is precisely the kind of fuzzy, probabilistic pattern-matching problem that geneticists encounter when aligning DNA sequences that have mutated slightly from one organism to another. Before computers entered the picture, the only way to find a match between 2 fragments was for a single scholar to have personally seen both pieces, or their hand copies, and to remember enough of the sign sequence on one to recognize it on the other, sometimes years later, sometimes in a completely different museum on a different continent. Generations of Assyriologists built their careers on exactly that kind of memory, carrying mental inventories of thousands of fragments, flipping through stacks of photographs and pencil tracings, hoping that 2 pieces excavated a century apart, stored on opposite sides of an ocean, might one day cross the same desk. So the EBL team borrowed directly from bioinformatics, building a tool nicknamed Cuneiblast, modeled on BLAST, the sequence alignment algorithm biologists use to compare DNA and protein sequences, and repurposed it to compare strings of cuneiform signs across tens of thousands of digitized fragments simultaneously, hunting for overlaps a human eye would never catch in a lifetime of comparison. The results were not subtle. In the roughly 150 years since Assyriology became a formal academic discipline, scholars working entirely by hand had managed to join about 5,000 cuneiform fragments to other known pieces, 5,000 successful matches in a century and a half of careful, exhausting comparative work. In the first 5 years of the EBL project alone, the algorithm-assisted team added another 1,500 confirmed joins, with several thousand additional likely matches still being verified. The pace was not just faster. It was categorically different, shifting a problem that used to take a research career to solve into one that could be approached in a matter of months. But finding that fragments belong together is only half the puzzle. The other half is knowing what they actually say. And that is where the story gets even stranger, because the most dramatic demonstration of what this approach could do involved not some isolated lost tablet, but an entire forgotten work of literature that had been hiding in plain sight, broken into dozens of unconnected pieces for over 1,000 years. In the ruins of the ancient city of Sippar, in the Temple of Shamash, archaeologists working with the University of Baghdad uncovered a library of cuneiform tablets. Among the team studying that collection, in collaboration with Jimenez and the EBL platform, was Iraqi archaeologist Anmar A. Fadil. Buried among the fragments was something that, on its own, looked like dozens of unrelated scraps. A few lines here, a damaged corner there, none of it individually significant enough to draw sustained scholarly attention. Using the AI-supported matching tools of the Fragmentarium, the research team identified that 30 separate manuscript fragments, scattered across the collection and previously treated as unrelated, were in fact all copies of the same composition. a 250-line hymn in praise of the city of Babylon, likely composed near the start of the first millennium BCE and used as a school text for roughly 1,000 years. Jimenez later said that identifying those 30 manuscripts as belonging to a single rediscovered hymn was a process that would formerly have taken decades of manual comparison. Instead, it took a fraction of that time. The reconstructed hymn to Babylon describes the city not in the language of conquest or politics, but as something closer to paradise. Its gardens, its abundance, the Euphrates flowing through its center, the prosperity of its people. It also reveals something unexpected about Babylonian values, passages addressing the protection of foreigners, the defense of the vulnerable, the freeing of captives and care for orphans, offering a portrait of moral self-image in the largest city the ancient world had yet produced. The findings were published in the academic journal Iraq, and they did something that pure speculation never can. They handed historians an entirely new primary source for understanding how Babylonians saw themselves, written not by modern reconstruction, but quite literally by Babylonian scribes, copied and recopied by students 1,000 years before the text was lost. That should have been remarkable enough on its own. Instead, it turned out to be one data point in a much larger pattern, because Babylon was not the only ancient script where artificial intelligence was quietly outperforming a century of manual scholarship. There's also a darker reason this race against time matters. Between 2014 and 2017, militants from the so-called Islamic State occupied large parts of northern Iraq, including the city of Mosul, near the ancient site of Nineveh and the nearby ruins of Nimrud. During that occupation, irreplaceable artifacts were deliberately destroyed on camera. Stone reliefs smashed with sledgehammers, statues toppled, archaeological sites bulldozed. Some of what was lost had never been fully photographed, transliterated, or digitized before it was destroyed, meaning a portion of that material is now gone permanently, not damaged, but erased, with no fragment left to scan and no digital record to fall back on. That loss became a turning point for institutions across the field. Digitization stopped being treated as a long-term academic convenience and started being treated as a race against an unpredictable future. A way of making sure that even if the physical clay was lost to war, theft, flooding, or simple institutional neglect, the information pressed into it thousands of years ago would not disappear with it. It is part of why projects like the Electronic Babylonian Library photograph, scan, and digitally archive every fragment they process, building a permanent record that exists independently of whatever happens to the physical object sitting in a drawer. 4 years before the hymn to Babylon was reconstructed, a separate but related breakthrough had already reshaped how historians thought about damaged ancient writing, not in Mesopotamia, but in Greece. In March 2022, a team from Google's DeepMind, working with researchers at the University of Oxford, Ca' Foscari University of Venice, and the Athens University of Economics and Business, published a deep neural network named Ithaca in the journal Nature. Ithaca was built to do something epigraphers had struggled with for 2 centuries. Take a damaged ancient Greek inscription, carved into stone or metal and missing words or entire lines due to erosion, breakage, or deliberate destruction, and predict what the missing text most likely said, where the inscription originally came from, and roughly when it was carved. The numbers were striking. Working entirely alone, Ithaca restored damaged Greek texts with 62% accuracy. That alone would have been a notable result. But the more important figure came from what happened when historians used Ithaca as a collaborative tool rather than a replacement. Historians working unaided on the same restoration tasks achieved only 25% accuracy. Historians working with Ithaca's assistance jumped to 72%, nearly triple their unaided performance. The model could also identify the likely geographic origin of an inscription with 71% accuracy and date it to within 30 years of the range proposed by expert historians, in some cases prompting scholars to revisit and redate key inscriptions from classical Athens that had stood unquestioned for decades. The lesson embedded in those numbers mattered far beyond Greek epigraphy. It suggested that the most powerful version of this technology was not a machine working in isolation, replacing the historian, but a machine functioning as a kind of vastly accelerated research assistant, one capable of holding the patterns of an entire corpus in memory at once, surfacing probabilities and connections, while the trained human still made the final interpretive call. That same philosophy quietly shaped how the Cuneiform projects were being designed back in Mesopotamian studies. Meanwhile, a separate research effort was tackling cuneiform from an entirely different angle. In 2023, a team from Tel Aviv University, Ariel University, and Heidelberg University, Guy Guthertz, Shai Gordon, Louis Science, Omer Levy, and Jonathan Barant, published a study in the journal PNAS Nexus describing a neural machine translation system built specifically for Akkadian. Rather than focusing on finding which fragments belonged together, the system attacked the translation problem directly, using convolutional neural networks to translate Akkadian into English in 2 different ways. directly from cuneiform Unicode glyphs into English, and from existing scholarly transliterations into English. For a dead language with no native speakers left alive to consult, and with a writing system as genuinely ambiguous as cuneiform, training a model to produce usable English translations automatically represented a meaningful technical leap. Not a perfect one, the researchers were careful to note, but one with high potential to assist both professional scholars and curious laypeople navigating texts that would otherwise require years of specialized training to approach. And the pattern kept extending outward. At the Persepolis Fortification Archive in Iran, a collection of roughly 100,000 cuneiform tablets and fragments written in Elamite around 500 BCE, discovered in 1933 by archaeologists from the University of Chicago's Oriental Institute, sealed inside a fortification wall of the ceremonial capital built by the Persian kings Darius and Xerxes. Researchers trained a separate machine learning system named DeepScribe. The archive itself is a bureaucratic treasure. Thousands of administrative receipts recording rations, travel permits, and labor payments across the vast Achaemenid Persian Empire, offering a granular day-to-day economic record found almost nowhere else in the ancient world. But its sheer administrative repetitiveness, paradoxically, made it both a perfect and a daunting candidate for automation. Perfect, because the formulaic structure of receipts is exactly the kind of repeating pattern a machine learning model can learn efficiently. Daunting, because the sheer volume, tens of thousands of small clay fragments, had made full manual cataloging impractical for decades. What made DeepScribe different from the EBL and Akkadian translation projects was its ambition to skip a step entirely. Most translation approaches, including the Akkadian neural machine translation system, still require a human-made transliteration as an intermediate step before translation can happen. Someone first has to look at the tablet and write down, sign by sign, which cuneiform characters appear, before any algorithm can touch the text. DeepScribe was trained directly on 6,000 hand-annotated images, covering roughly 100,000 individual signs, with the goal of using computer vision to read cuneiform directly from a photograph of the clay, no transliteration required, essentially attempting to teach a machine to look at a tablet the way a fluent scribe once did 4,500 years ago, recognizing the wedge-shaped impressions themselves rather than a human's prior interpretation of them. Each of these projects, built independently by different teams in different countries working on different ancient scripts, was converging on the same underlying realization. The bottleneck in understanding the ancient world was never a shortage of evidence, it was a shortage of time. Hundreds of thousands of tablets sat undigitized and unread, not because nobody cared what they said, but because no group of human scholars, however dedicated, could process that volume of fragmentary, ambiguous, physically scattered material within a single career, let alone several careers strung together across generations of fading institutional memory. It would be a mistake, though, to treat any of this as a story of machines simply replacing human judgment, and the researchers behind these projects have been consistently careful not to frame it that way. The DeepMind team built Ithaca explicitly as a collaborative tool, and its own data proved why. The model alone was good, but historians plus the model were significantly better than either working separately. The Akkadian translation researchers were equally explicit that their system was meant to assist scholars, not bypass them, describing a future scenario in which the model would even show its sources to support transparency and trust. Jimenez and the EBL team built their platform around a public, searchable database, specifically so that human Assyriologists around the world, not just the project's own staff, could verify, challenge, and refine what the algorithm proposed. Every fragment identified by QNABLAST as a likely match still requires expert confirmation before it enters the scholarly record. The machine narrows the search from an impossible haystack down to a handful of likely needles. The human still has to recognize the needle when they see it. There's a reason for that caution, and it is the same reason that applies to any language model asked to fill gaps in a damaged text. Confident, fluent output is not the same thing as correct output. A neural network trained to predict missing or ambiguous cuneiform signs is, at its core, predicting the statistically most probable answer based on patterns it has seen before. And a statistically probable answer is not guaranteed to be the historically true one. An inscription could plausibly be restored in a way that reads smoothly, makes grammatical sense, and is still simply wrong, especially in cases involving rare vocabulary, an unusual scribal hand, or a genuinely unprecedented event the model has never encountered in its training data. This is precisely why the strongest results so far have come from human-machine collaboration rather than machine output taken at face value, and why every reputable project in this space treats algorithmic suggestions as a lead to investigate rather than a verdict to publish. That distinction matters enormously when separating verified discovery from speculation, because the temptation in any story about artificial intelligence and lost ancient texts is to leap straight to the most sensational possibility, that somewhere in these unread fragments lies a tablet that rewrites history entirely, a flood narrative predating Genesis by 1,000 years, evidence of contact between civilizations historians say never met, a king list extending Mesopotamian chronology back further than currently accepted. It is worth being honest about where the evidence actually stands. No verified discovery to date has overturned the broader timeline of Mesopotamian history, or revealed a forbidden narrative the field had been suppressing. What these tools have produced instead is something arguably more valuable, if less cinematic, a measurable accelerating recovery of texts that were always part of the historical record, just physically scattered and practically inaccessible. Texts like the Hymn to Babylon, which didn't change what we knew about Babylon's existence, but transformed how much we understood about how Babylonians saw their own city, their own values, and their own place in the world. Still, the unresolved questions are real, and researchers in the field are candid about them. Nobody currently knows how many more compositions like the Hymn to Babylon are sitting unidentified across the world's collections, broken into pieces nobody has yet matched. Some estimates suggest only a small fraction of known cuneiform fragments have been fully digitized and cross-referenced against the rest of the corpus, which means the pace of discovery over just the past several years may represent the earliest phase of something much larger, rather than a peak already reached. There is also an open question about how far automated translation can go without human oversight, whether systems like the Akkadian neural network or DeepScribe's computer vision approach will eventually reach a reliability threshold where they can responsibly operate with less supervision, or whether the inherent ambiguity of a 4,000-year-old writing system will always require a trained human mind as the final check against confident, fluent, but ultimately incorrect machine output, a risk every team working in this space has acknowledged directly. A further question concerns funding and access. Tools. This power will require sustained investment, server infrastructure, and ongoing collaboration between institutions in wealthy countries and the museums and archaeological authorities in Iraq, where most of this material was originally created and where the expertise to contextualize it culturally and historically remains deeply rooted. How equitably that collaboration unfolds, and who ultimately controls access to a fully digitized record of ancient Mesopotamian civilization, is itself an unresolved question with no fixed answer yet. What is not in question is the trajectory. A century and a half of Assyriology produced 5,000 fragment matches. 5 years of AI-assisted comparison nearly matched that entire historical total on its own, while simultaneously helping reconstruct lost literary works, accelerating Greek epigraphic restoration to nearly triple unaided accuracy, and opening a translation pathway for a dead language that has had no native speaker for roughly 2,000 years. Multiply that trajectory across the remaining unread fragments still sitting in museum basements in London, Berlin, Istanbul, Philadelphia, and Baghdad. Fragments excavated more than a century ago, transliterated by hand, if they were processed at all, and never compared against the rest of the corpus because no human researcher ever had the time. And the implications stop sounding like science fiction and start sounding like an inventory problem on a civilizational scale. Somewhere in those drawers, in collections that have not been fully cataloged, let alone cross-referenced by a system capable of holding hundreds of thousands of fragments in active comparison at once, there are very likely more compositions like the Hymn to Babylon waiting to be reassembled, administrative records that could reshape economic history, omens and medical texts that could rewrite the history of ancient science, royal inscriptions that could resolve open chronological debates, prayers and letters that could put names and voices back onto people who have been silent for 4,000 years. Nobody can say with certainty what they contain because, by definition, nobody has read them yet. That is not speculation built on hope. It is a direct mathematical consequence of how much of this material still remains unmatched, sitting exactly where it has sat since the 19th century, waiting only for someone, or something, to finally have the time to look. It raises a strange, almost vertiginous thought. Every one of those scattered fragments was once a complete object, a tablet a scribe could hold, read aloud, file away, or hand to a student to copy as a lesson. Somewhere along the way, fire or flood, or the simple collapse of an empire, broke that object into pieces, and those pieces scattered across the earth, surfacing again only when 19th century excavators, working largely by intuition and shovel, happened to dig in the right place. The fact that any of it survived at all is itself improbable. The fact that 4,000 years later, a different kind of mind, not a human one, but one shaped by human research into how human language and human writing actually work, could look at the scattered pieces and begin reassembling them is something closer to strange. The scribes of ancient Mesopotamia could not have imagined that the clay they pressed their reed styluses into would still exist 4,000 years later. They certainly could not have imagined that the language meant to outlast them would go silent for 2 millennia, only to be coaxed back into speech not by another human scribe, but by a different kind of intelligence entirely, one built from silicon, trained on the patterns of the very writing it was meant to decode. The question this leaves behind is not really about the machines at all, it is about us, and about how much of our own deep past has simply been waiting in the dark, fragment by fragment, for someone to finally have the time to listen.